All right, so let's do a little more with just the basics, and then we want to apply this to the Duhamel situation of an actual differential equation. So what's going to be the derivative? So you take delta prime and you convolve it with g. What is that going to be? Well, now that's very easy, just a manipulation. That's the derivative of delta star g. Well, that's just g prime. So that's kind of interesting. You can think of differentiation as convolution with delta prime. And I want to say a few things about that. One is that integration, we already knew that that was convolution with something. If you take h star g, the Heaviside unit step function of t, that's the integral from minus infinity to 2. So it's the running total from the very far past of g. So it's g of tau d tau. So it's one antiderivative, it's a particular antiderivative of g. So integration or antidifferentiation is convolving with h. The identity, doing nothing to a function. It sounds kind of silly to have a complicated interpretation of that, but it's cool. It's convolving with delta. And then delta prime star g is the derivative. And similarly, and this is, I think, problem 8. Yes. The nth derivative of the delta function star g is the nth derivative of g. So everything in one variable calculus is a convolution. Integration, differentiation, multiple differentiation. And this is not something I included in the PDF, but let's see why that would, another way to make this plausible. Again, we can go back to the idea of approaching distributions from honest functions. So this guy is close to delta prime, this kind of down-up pulse. And what happens if you convolve that with a function f? Okay, you're going to take that and you're going to flip it and scan it across the function. And in terms of, say this is like epsilon minus epsilon. And so you're going to get delta prime. So, well, not delta prime, but let's say this is, ooh, you know what, let's call this g, and let's call this f sub epsilon. You're going to take f sub epsilon star g of, I've been using t and tau consistently because I'm looking forward to doing this with Duhamel's principle. Okay. That's going to be, well, you know what, I need more room. Okay, so f sub epsilon star g of t. I'm not going to do this in gory detail, I think, but I want to get to where it's plausible. So that's going to be the integral minus infinity to infinity of, oh, and that's what's wrong here. I knew I was going to get the wrong sign. If I look at the derivative of like a hump, it goes up first and then down. Hopefully you were noticing that. You're like, wait a minute, that's wrong. Okay, that's really what delta prime looks like. Because remember, delta is kind of an up pulse, then down, and so the derivative should be up and then down. Okay, so now it's going to be that integral of f epsilon of, and I'm going to put the tau on that guy, g of t minus tau d tau. Oh, and this has to be, what was it? It's 1 over 2 epsilon squared, I think. I might be getting the 2's wrong. I wasn't intending to do this, but it just struck me as something I should do. Okay. So that's going to be 2 integrals. It's going to be the integral from minus epsilon to 0 of 1 over 2 epsilon squared g of t minus tau d tau. And then minus integral 0 to epsilon 1 over 2 epsilon squared. Okay, so what is that going to do? This is going to give us an average of g, a scaled average of g for values that are just a little bit bigger than t, because I'm taking t and I'm subtracting a small number, small negative number epsilon. So this is going to be g at a little bit past t, or maybe let's say about t plus epsilon roughly. Okay, this is going to give values at g of t minus a positive number. This is going to be stuff like g of t minus epsilon. Okay, now this is only over a region of width epsilon, so you get a factor of epsilon for that small width, but then that cancels one of the factors here. And so I get something like 1 over 2 g of t plus epsilon minus g of t minus epsilon over epsilon. And that's the symmetrized derivative. And that converges to g prime of t. Okay, didn't do that too carefully, but the idea is that when you scan this guy across a function g, then and let epsilon go to 0, it will converge to g prime. So we could have done that a long time ago and not mentioned, oh, hey, secretly, this is, you think of this as an approximate fixture of delta prime. So anyway, that's another really good reason to believe this is not just formal, this is not just games. It's very pretty games if you consider it that way, but it really makes sense. Okay, so now I want to look at, I won't get all the way to the proof of Duhamel, but this is a good time to introduce some notation so that we can be a little more general here. When we keep writing out, I'm just getting sick of writing this out, this whole thing. And the details, right now, the details are really immaterial about how many derivatives am I taking, what are these coefficients, what are they called, and so I want to generalize that a little bit. So I want to get to the idea of an operator, and specifically a differential operator. Okay, and that's just what happens when I take anything, function or distribution, doesn't matter, and take that and put it in the machine that outputs something like this. Okay, the simplest gadget like that would be just take u and I output u prime. So I want a name for that gadget. Now the cool thing, there's a level of sophistication here. This is, let's say these are functions actually. I usually use u for distribution, so let's say like g. I don't want to muddy the waters, I don't want to make it look too complicated. Let's just say we've got a machine that takes functions, and they have to be pretty decent functions in order for this to work nicely, to take derivatives and things like that, to functions. And if I want to be really very precise, let's work with test functions, because we know nothing ever screws up with that. Derivatives and integrals never screw up with that. And you can certainly take the derivative of a test function and you get out another test function. That's the nice thing about infinite differentiability. You don't lose a degree of differentiability. Okay, so to be specific, we can think of it this way. Really, morally, you can just think, as long as this is plausible to take a derivative, it's just taking a space of functions to a space of functions. Okay, well, let's have a name for this. Let's call it big D, the derivative operator. And depending on what you've seen before, you might have seen this idea of taking this process of taking the derivative and realizing that that's a function whose inputs are real valued functions on the real line. So it's a level of abstraction up. If you do computer science, that's a fairly familiar concept. A function that eats functions, it spits out other functions. Okay, and that's one example, the derivative operator. So the definition is simply that it takes a function and differentiates it. But we could call this guy something else. We could call that L for linear differential operator. It's just defined to be the thing that takes G and spits out this combination for some coefficients M, C, and K. Okay, so the L is going to depend on the M, C, and K, but I'm not explicitly indicating that in the notation. Okay, so in general, LG is going to be something like C. No, I guess I had A, like A sub n G nth derivative plus A n minus 1 n minus first derivative plus down to A1 G prime plus A naught G. Notice I'm not including just like a constant. It's all derivatives of G or just a multiple of G itself. That's to make this homogeneous. Remember, if we put in something over here like 5, or if we put the 5 over here, that's an inhomogeneous equation, and it's not really a linear expression. I think my camera has moved a little bit. Okay, sorry about that. I'm not getting the whole screen anymore, the whole whiteboard. Okay, so this is the kind of expression I'm talking about, and so that's another example of a differential operator, and it's linear. Really important is, just based on the basic principles of derivatives and things like that, is that L of f plus g is LF plus LG. And L applied to a constant times f is C times LF. Very important. Okay. And oh, notice what I'm doing here. I'm using something that we often do for linear functions, and things like sine and cosine too as well, or log, is I really should be writing parentheses every time, but we often just drop the parentheses. It's kind of dangerous because, for example, if I do L, F, G, and F and G are both functions, okay, let's think about what that is. Okay, that's a bit ambiguous because let's say the derivative, for example, let's look at that, the simplest interesting differential operator, just plain the derivative. That's the derivative of fg, so that's f prime g plus fg prime, or in this fancy notation, it's d applied to f times g in the ordinary way, multiplying functions, plus f times dg. Now, if you just wrote dfg without any parentheses, you don't know whether you mean this, do the product first and then take the derivative, or this, take the derivative of the first gadget and then take the product. And they're different by this much. So be careful about that, even though this suggests we might not have to be. This is not multiplication by L. It is applying a differential operator, which is more interesting. Now, in the PDF, I mentioned that theoretically we could have these be functions as well. And that's still called a linear differential operator of order n. But for us, we want constant coefficients. So these are going to be real numbers. They can be made complex very easily, but I'm trying not to be overly general in all these lectures. Okay. And the reason we need constant coefficients is that those are things that don't change when we slide and translate. We get the symmetry principle. And Duhamel's principle only applies to constant coefficient differential operators. So what that allows us to do is just to formalize what we're saying and generalize it really quite easily. Okay, we're looking at, so here's what we want to show, and then I probably will postpone showing the next one. Actually, I don't know. I'm going pretty fast. Yeah, let's get to the punchline. Yeah, let's get to the punchline. Duhamel claims, okay, here's the claim, that if, so I've got any, it really applies to any constant coefficient linear differential operator. If U is some special gadget, well, right now I'm only assuming it's a distribution. Very often, I mean, really, in any kind of case like this, it's going to be a function, unless U is very, very special. But I don't want to have to assume that, because I don't have to prove it right now. Okay, so U is some distribution, and L can act on distributions clearly as well as it can act on functions. It's just differentiating, addition, and then multiplying by constants. So if it solves this problem, then y equals U star f solves the more general problem. It's a very, very elegant way to talk about everything that's been motivating us so far. This can be the second order differential operator that's about springs and RLC circuits. It could be a first order differential operator. It's about exponential growth and decay, basically. It could be a 10th order differential operator. There's really nothing different. So this is one of those cheap generalizations we might as well do, even if we're trying not to be too general. Okay, and we're almost there. We've set up enough beautiful machinery, lots of work, I know, to make this really easy. So the first thing is just number 9. The claim is that L of U star G, with no assumptions about U right now, no matter what I have, if that's a distribution and that's a function, then that's just LU star G. Why is that true? This is just the sum. Sums never bother us. We're doing linear stuff. If we weren't doing linear mathematics, they would bother us. It'd be a big deal. Of coefficients times derivative operators repeated, so d squared, of course, is just the second derivative operator, things like that, of U star G. But the derivatives go in here, and the constants go in here, and the sums go in here, and so that's just the sum of AK dKu. Just put them all on the first factor, star G, but that's just LU star G. Oh yeah, it's right there. Okay. So we've set this up in a way that this is easy. That we knew there was a real proof that derivatives and convolutions treated each other well. That meant it was easy to define the convolution of a distribution and a function so that derivatives treated it well. Constants and sums are never a problem. And so everything works. Okay, so that's very cool. Now, again, um, if we had if these guys were functions and actually variable, then as soon as we start interacting with that with convolutions, it would be much more complicated. Okay, so okay, so now we're almost done. And definitely, if you've never pressed pause and tried to solve yourself, now's the time. Okay, we're going to now assume in just a few minutes ago, we weren't assuming anything special about you. It's a very general principle that you can just take linear operators into a convolution on either side, and even if one of the factors, or really both of the factors, is a distribution. Okay, and now we're going to assume something very special about you, that LU is delta, that it's a fundamental solution for whatever this operator is. So it's the response to a hammer blow in the spring. It's a response to a sharp pulse in a RLC circuit. Okay, so if that's true, then we're just going to take Ly, L of U star F. We're going to bring that LU in. That's delta, and that's F. And that's it. That's the proof of Duhamel's principle, at least in the setup that we've got. Now, it's really formal. Some people love that kind of beauty, and some people are like, I don't believe we just proved anything. Well, but it works this formally because the machinery is kind of hidden in it. Okay. Now, what have we assumed? We have to assume here we don't know how to do this yet, where this isn't a test function. So this had to be in test functions. That's not very satisfactory because, for example, a lot of the forcing functions that we were dealing with, which is to really get intuition about this, were like non-continuous functions, like rectangular pulses. And with the RLC circuit stuff, we looked at like solving Ly equals delta prime, things like that, where it's a distribution and even not the simplest distribution. Okay, so that is unsatisfactory at this point. All we know how to do, all that Duhamel tells us right now, is that if you solve it for this particular funky gadget, a distribution, a hammer blow, then for some reason we've then backed off and said all I know how to do is the response to some really nice limited, compactly supported, and smooth pulse of forcing. But soon we'll be able to generalize this. We've really got the ingredients. But this is great. We've got a really good start. Closes a circle of ideas for me in terms of getting to at least one version of this big principle that's super, super practical. The rest of the handout is going to be just a few examples, really kind of toy examples, not super challenging ones, of using this and just trying to make it more concrete before we get back to the theory. All right.